Okay, General Chemistry 2 class. This is the video for Wednesday. Oops, guess I'm not on Airtame yet. Let's see, Airtame. Come on, Airtame, where are you? There we go. Share window, 2849. There we go. All right, here we go. There we are. Here we go. Perfect. All right. All right. We'll claim victory when we can. This is the video for Wednesday, March 3. As far as the announcements go, the two sections of Alex homework. One is due Wednesday night. That's scheduled for March 3 tonight, and the other is for Sunday night. Don't forget, Alex, keep working on it. Lab for this week. If you've got lab Thursday, make sure that you check the new document that's on Moodle for your lab course. And there are 2 videos associated with that. Make sure you look at those as well. The 2 worksheets, worksheet 11, make sure you upload that by Wednesday night, and worksheet 12 by Friday. And then finally, the exam 2 is coming up next week. Tuesday, March 9th at 5, Wednesday, March 10th at 12:30. Despair, little despair today. It's not just the ability to put a plan into action, it's our solution for those who lack that ability. It's pretty harsh. Refuse to accept anything but the very best, and you're never going to last around here. One of those business despair slides. When your best just isn't good enough. Until these go alphabetically. It's your destiny. Ouch. Until you have the courage to lose sight of the shore, you will not know the terror of being forever lost at sea. And finally, those who say it cannot be done should not interrupt those busy proving them right. Which leads us to chapter 16. This is the last day on equilibrium. We're going to go through several types of equilibrium problems today. Among the basic principles with an equilibrium reaction, you start with reactants, or you typically start with product. The reaction goes until you end up having this back and forth, this dynamic where the rate forward equals the rate reverse. We ended with this particular calculation. This is the reaction we'll be doing in lab next week. And given this problem, we start with this and this. They're mixed. At equilibrium, that concentration is determined. So, at this stage, what do? We plug in everything that we know. We know the initial concentrations. This is 0. We're not given any information about it. The change, set up your ice table. Initial change equilibrium. We know this. We know the change that occurred. Therefore, we know the change here and here. All of our coefficients are 1. So notice that the change here is plus 0.1. Therefore, this change is minus 0.1, minus 0.1, because this reaction goes from left to right. We lose material here. We gain material here. Please include the plus and minus signs as you go through these types of calculations. Let's look at this problem. And of course, let's see if I can do this. Yeah, probably not. We can record this. I want to move this. Oh, that's really bothering me here. There we go. Okay. Let's go back. And did I lose it? Yep. Need to go back to Airtame. Window. There we go. All right, here we go. Yeah, this is our equilibrium sign here. It needs to stay there in the middle. Now, notice what's different here is that we already know the value of K from the previous problem. Because once we know K for this reaction, that equilibrium constant holds no matter what the concentration. If we change the temperature, that will change the value of K. But it could change the value of K. But for what we're doing here, K is the same. We have different starting concentrations. We now know the value of K because it's been calculated. What is the equilibrium concentration of this? Excuse me. We're not given any initial concentration. Now we're asked to find the equilibrium concentration. Now this is a typical kind of problem. Let's see. Nope, let's stay with this slide. This is the only problem we're going to do here. There's an extra one, but I'm not going to go there. All right, so let's talk about this. I'm going to set up the ICE table up here instead of below, just because I want to keep this material up here, this writing up here. The original concentration is 0.100. This is our initial. Let's see, for thiocyanate, 0.150. And over here, 0. Happens every time, doesn't it? The change. And then the equilibrium concentrations. Now, we don't know what the changes are. We know the stoichiometry. So normally we'd have the reaction up here at the top. We have the reaction, then we have initial concentration, equilibrium for our ICE table. We do ICE tables for equilibrium problems. We do know K. K is equal to the concentration of Fe, SCM, 2 plus, all over the concentration of Fe3 plus, and SCM minus. So this is the equilibrium constant expression for this reaction. Coefficients are all 1, exponents are all 1. And from before, we know this has a value of 40. If you have questions about where this number came from, look at the previous lecture. So the change that occurs, we know that reactants have to be moving to the right to form product because we don't have any product here to start with that can go back and form reactants. So we're going to lose, and gain. We use our minus and plus signs. That indicates the direction the reaction is shifting to move toward equilibrium. How far does it go? We don't know, because that's what we're trying to find. We're going to say that how far it goes is x, some variable. And so if we gain x here, we're losing x here, and we're losing x here because coefficient is 1. For every mole we gain, we lose that same number of moles from each of those two. At equilibrium, we add the initial plus the change to get the equilibrium rate. There we go. We now have our equilibrium concentrations of each thing. And I can plug them in. So 40, our value of K, is equal to the concentration of our product, X, all over the concentrations of the reactants, 0.1 minus X, and 0.150. Now what we do is we have an equation with X as the component. We just solve for X. How do we do that? Well, there are a couple of ways we can. What I'm going to do is move this, the denominator, over here. All I did was took the denominator, multiplied both sides by it, and now that's equal to X. So here's what I'm going to do. There are two ways I can approach this. Actually, there are a lot of ways I can approach this. But one thing I'm going to do is, for me, I'm going to try to avoid using the quadratic expression. So I'm going to work this two ways. I'm going to try solving it without using the quadratic expression. Then I'll come back and work it using the quadratic expression. So if you recall from the last problem, which I'm sure you do because you've got your notes in front of you and you're studiously scribbling notes as we go through here, the change that occurred was around, I think it was around 0.1. These were both 0.15. So let's just say, I think we ended up with 0.05. So let's look at these numbers. I can lose 0.05. I can lose 0.05. This could gain 0.05. Let's just see what that gives us. So if I plug in numbers 0.05, I'm going to do 0.050. I'm going to plug numbers to the x's that are subtracted from other numbers and see if that gives us the same value over here. So I'm going to pick 0.05 as my input x. In other words, so you see what we have here? Just take a look at this equation for a moment. This equation right here. Yeah, this one. The one I'm about to get to. Here we go. If we look at this equation, what I'm doing is I'm looking at the x's that are subtracted or added to other numbers. And then I can solve the problem and then see if it matches the x that I put in. I'll get a number for x. Is it the same as this? That's the principle. This is called the method of successive approximations. I'm putting in a number, saying, hey, this could work. I'll approximate it. Does it give us the same value? Well, let's try it. So I'm going to use the calculator on my phone to do this. So for 0.05, 0.1 minus 0.05 is 0.05, 0.05. 0.150 minus 0.05 is 0.100 times 0.100 times 40. And I get a number of 0.20. I started with 0.05, I got 0.2. I was hoping to get the same number. Hey, that was the first go. Let's try something else. So I want this number that I put in to be just a little bit higher. I don't want to go lower because if I go lower here, this is going to end up higher here. So I'm going to try something like, I don't know, 0.07. Let's see what 0.07 gives us. So if I plug in 0.07 instead of 0.05, if I plug in 0.07 for the thing in parentheses, 0.1 minus 0.07, that's 0.03. And if I plug in 0.07 here, 0.150 minus that is 0.08. Now I have 40 times this number times this number. Does it give me x? So 40 times 0.03 times 0.08. 0.096. So if you take a look at these two numbers, this number and this number, now I raise this number is a whole lot closer. I'm converging. So I'm converging. I want them to be the same. So they're not a lot different. I'm going to try one more number. Let's try 0.075. If I go 0.08, see this is a big jump from 0.05 to 0.07. That brought this down from 0.2 all the way down to less than 0.1. So if I do 0.075, what do I get? 0.1 minus 0.075 is 0.025. See, this isn't really that hard to do. I'm just kind of making up numbers until the calculation on the left approximates and equals the one on the right. 0.075, 0.150 minus 0.075 is 0.075. 40 times this times this. Let's see what we get. .075. So you see my points converged. By using the number 0.075 for x, the whole left side of the equal sign is equal to 0.075. The numbers came out the same. What that tells me then is that this is the answer that I am looking for. Now, was it easy to get? It took me 3 iterations. Maybe it could take 4 or 5 or 6. By the way, what if I had used a number like 0.04 instead of 0.07? What if I went the other way here? A number smaller than this? This number would have been like 0.3, 0.4, something much higher. In other words, those numbers are going to diverge. I wanted to number in, number out. I wanted something that was kind of in between. So I kind of worked my way up, and I got lucky with 0.075. This took a few minutes. It would have taken a lot less if I weren't explaining it. But now what we can do is take a look and see how to solve it by using the quadratic expression. And what I'm going to do is work that over here on the right side. So the quadratic expression is basically taking this mess and putting it into an equation and then solving it. X is equal to minus b plus or minus, yeah, that thing. So I'm going to do this. I'm going to pull this out over here, set that equal to x. So I'm just going to take this equation that I had, which came from here, multiply both sides by this whole denominator, and I'm going to work that out here. So 40 times 0.100 minus x times 0.150 minus x is equal to x. So I just recopied it. Now what I want to do is multiply this out. Multiply it out. So the first thing we do is multiply these two, and then we add this times this, plus this times this, plus this times this. So we kind of multiply each of the components times each other. So this is 40 times these two times each other, 0.1 times 0.150. This times this is 0.0150. Then we take this minus 0.150 minus 0.100x minus x times minus x is plus x squared equals x. Can you see that? Okay. These two are the same x terms, so this is now 40 minus this minus 0.15 minus that is minus 0.250x plus x squared plus x. In order to get this into quadratic form, I need to get ax squared plus bx plus c is equal to 0. Okay, now I need to pause this. Let's see. Pause this. And I need to shoot. Recording. Here we go. Paused. All right, there we go. Sorry about that phone call. That was reasonably important. And here we go. So hopefully just fast forward through all this stuff that really doesn't seem to make too much sense. Okay. Now let's come back to this. And we were working on our lovely quadratic equation, I believe. And okay, so we've got to this point. Now let's just multiply everything through by 40. My calculator back. 0.015 times 40. This is 0.6 minus 0.25 times 40, which is 10. So good for leaving this open. 10.0x c plus 40 x squared is equal to x. Okay, so I just took this, multiplied every component by 40. I get this. Now I need to convert this to 0. So I'm going to put this in typical A, B, C format. 40x squared minus, subtract x from both sides, minus 11x plus 0.600 is equal to 0. Now I can just take these numbers, I can divide by 40, I think at this point, what I'm going to do is I'm just going to use these values for A, B, and C, plug them into the quadratic expression. So this is my value for A, B, and C. All right, so let me set that up. Switch, this might have a little more ink in it. So X is equal to negative B plus or minus square root of B squared minus 4AC all over 2A. Now I plug the numbers in. Negative B is minus 11.0. So this is 11.0 plus or minus. Let's see, 11 squared is, I believe, 121. Minus 4 times A times C all over 2A, which is B. So this is equal to 11. Let's see, 121 minus 96. So this is 121 minus 96. $25. And the square root of 25 is 5, I believe. So this is equal to 5. So this is 11. So the square root of 25 is 5. So the whole thing here is plus or minus 5. Get the blue back. This is all over 11 plus 5 over 80. So 16 over 80, 0.20. This is 11 plus 5 over 80, that's 0.20. 11 minus 5 over 80 is 6 divided by 80. 0.075. So you recall that 0.075 is our correct answer, but we get two answers by solving the quadratic expression. And the thing is, one of them does not make sense. And why doesn't one of them make sense? Let's look at the 0.20 number. That's our one option. 0.1 minus 0.2, we can never have a negative concentration. That's why that doesn't make sense. 0.15 minus 0.2, that also would be a negative concentration, so that doesn't work. So X is 0.075 because of these two answers, only one of them physically, logically makes sense. Okay, so I've worked this two ways now. I have worked this two ways, and now you know why I prefer to use the method of successive approximations, where I plug in the numbers and see if I can work my way through like this, as opposed to doing the quadratic expression. Now, if you feel more comfortable doing the quadratic expression, you can do that. My goal is not to have to use the quadratic expression a lot. Whew. I don't know about you, but my brain hurts a little. Okay. We're going to skip this. Yeah, that's worksheet 12. I'm going to jump right to this. Do I want to jump right to that? Yeah, I'm going to jump right to this. Okay. Well, let me get rid of all this stuff. Right. Okay, here we go. Well, now that I'm thinking of it, we may not finish the whole thing today, but we're going to at least make some good progress, folks. All right, let's take a look at this program, this problem. Here we have a reaction, and we're given K. Determine the equilibrium concentration of each species given. We are given the initial concentrations of the hydrogen and the fluorine. So here's our reaction. We're given the same quantity of these two things to start with. determine the equilibrium concentrations of each species. So we do this. It's like before. We're going to set up an ice table. Let's do this one in green. I'm going to do the ice table down here. So with hydrogen, our initial hydrogen, so let's see, I, C, E. Initial 0.258. Initial 0.258. And for HF, 0. So I'm just trying to, guess I could move that over a little bit. This right here. Oh boy, getting a little sloppy there. Okay. So 0.258. Now we have K. That's a big thing. We know K. We're going to treat this a lot like the problem that we just did. The change that occurs, well, you have 1 mole. So first of all, we know it's going from left to right. By the way, we could be going from right to left and have the same thing and work it the same kind of way. I think we'll do that next. So we have these two. We know it has to go right because there's no product to go left. Minus X. And now we have a coefficient of 2. So for every mole of this that reacts, we form 2 HF. For every mole of this, we form 2 HF. 1, 1, and 2. So here we go. 0.258 minus X, 0.258 minus X, and 2X. These are now the equilibrium concentrations of each of our components. And we know our value of K. There's only one X. I mean, there's only one variable, that's X. X is how far the shift happened. How far did this go to the right? So let's plug this in. 389 K is equal to this concentration squared at equilibrium. This is the equilibrium concentration of HF. That's where it goes. It's equal to 0.258 minus X. 0.258 minus X. I plug everything in. I can do the method of successive approximations. I can solve for X by the quadratic, but it's not quite that hard. If I redo this, this is equal to 2X, the quantity squared, all over 0.258 minus X squared. In other words, we have the same thing times itself. Now I have a number, a squared term, and a squared term. So now all I have to do is take the square root of both sides. So the square root of 389 is equal to 2x, because remember, it's only the square term that goes away, all over 0.258 minus x. Now, it is a much simpler problem to solve. We don't have any x squared terms. We don't have to use a quadratic. We just took the square root of both sides. It comes very clean, like this. And now all we have to do is multiply and solve for x. 389, and let's see, the square root of that is 19.7. I'm going to continue to use the white space up here, I think. So what I'm going to do is multiply this denominator times 19.7, 19.7 times 0.258 minus x is equal to 2x. Took this, multiplied both sides times this denominator to get rid of it on the left and move it over to the right. Now we just multiply this out. It's 19.7, 19.7 0.258, 5.09 minus 19.7x equals 2x. I'll combine the x terms, add 19.7x to both sides. 5.09 is equal to 21.7x. X is equal to 0.234. So the key here was being able to do the square root of both sides. They happen to be the same. If this initial concentration hadn't been the same for both, I couldn't have done this clean square root thing because this number would have been different from this number. But since they're the same, it works out nice and clean. Now I have this value for x. The question is, determine the equilibrium concentrations of each species. 0.258 minus x, 0.258 minus 0.234. This is 0.024. 0.024. And then 2x, 2 times that is 0.468. These are the molar concentrations of each of these components at equilibrium. That's a beautiful thing. So how do we do it? Let's think about this problem. Erase all of this. I'll keep the basic ice table because we'll use it again. So here's the next problem. Same reaction, same K. Determine the equilibrium concentrations of each species given this, given 0.258 molar HF. This is our product now, and we're going to work this problem in reverse. So we end up with our initial concentration for HF, 0.258. That's all we are given. We have 0 hydrogen, 0 fluorine. We are only given a product. If we had been given these products, that would have been indicated in the problem. If we'd been given these reactant concentrations. So we have this. The reaction goes from right to left. Don't forget the -2. We have a coefficient of 2 there. And we're losing x there, we're gaining x here, we're gaining x here. So we get x at equilibrium, 0.258 minus 2x. So we take these equilibrium concentrations, plug them into our equilibrium constant expression. 398, 389 is equal to 0.258 minus 2x. And that is squared. Remember, so it's not only the 2x here that comes into play, it's also this whole concentration squared in the equilibrium constant expression. The easiest place for people to get messed up, right here, for getting the 2, and right here, for getting the 2 up here. And this is all over x squared. We have the exact same scenario we did before. We have a squared term over a squared term. So this becomes the square root of 389, what was that, 19.7? Is equal to 0.258 minus 2x all over x. And now you just solve this for x like we did before. So this is 19.7x equals 0.258 minus 2x. Add 2x to both sides. x is equal to, this is going to be a pretty small number, 21.7 divided by 0.258. Sorry. It's the other way around, actually. Let's see. So it's 0.258 divided by 21.7. Seven. 0.011 or 0.012. So at equilibrium, we know what x is. 0.012, 0.012. 0.258 minus 2 times 0.012, 0.024. 0.024 subtracted from this is 0.234. And voila, we have our equilibrium concentrations. Okay, we are going to start with, this should get you through a good part of worksheet 12. And we're going to pick up here for the lecture on Friday.